Okay. Okay. Let's get started with today's lab. Actually, before starting this class, I will introduce about the lab assignment, new lab assignment. Then I think it was posted on the blackboard because I scheduled to post this lab assignment at 10:30 exactly. So actually, in the third lab assignment, you are requested to design FSM, but don't worry because I think you are very familiar with this FSM because we learned this state transition during the lecture, right? So actually, I will not explain about this transition diagram because I think you are very familiar with this figure. Okay. Actually, there are only two tasks for this lab assignment. For the first task, you need to design a simple FSM. So actually, and then generously, so I made the skeleton code of this FSM. So you can just design three basic blocks of FSM. What are three basic blocks? State register, next state logic, and after logic, right? So you can just design the simple FSM based on the state transition diagram. Also, actually, during the lecture, so we just defined the state height, but I found that the state height does not work well in using the Descartes variable. So I just define the parameter. So actually you can see that this local parameter. So it means that this is the local parameter. Then it just define this string equivalent to 2 bit 0 0. Okay, like the S0 is equal to 2 bit 0 0, S1 is equal to 2 bit 0 1. So actually you can use this character for representing state. Okay, so you can use the S0, S1, S2, S3 like the example and the example we learned during the lecture, right? Also, you can find another parameters like the green, yellow, red. So this is equivalent to this value, right? So you can also use these parameters like green, yellow, red from this design. And then I believe if you understand the FSM design we learned during the class, then I think you can easily do this task. Okay. And then the second task is also so you are requested to design vector FSM. So vector FSM. So we also learned about the vector FSM during the lecture. So we can divide the complex FSM into multiple sub-FSMs. So which means that using the vector FSM mechanism, and we can design FSM more easily. So we can design the simpler FSM, simpler multiple FSM. So this is also, I think you are familiar with this transition diagram because I also covered this FSM during the lecture. So there are two FSMs, and then in the module, then we need to include these two FSMs in the top module. So I will also show the skeleton code of the FSM2. So FSM in the FSM2, you need to design this vector FSM. So if you see this skeleton code, then you can find the FSM mode. So in the FSM mode module, then you need to design which FSM, this mode FSM. So you need to design mode FSM in the FSM underbar mode module, right? So actually I define the required port here, and then so also you can design 3 basic blocks of this mode FSM, and then likewise, so you can find another module FSM underbar light. Okay, so under this FSM underbar light module, then you need to design light FSM. Okay, so actually this FSM is very similar to the first FSM, right? Actually the condition is a little bit different here. And then you need to also connect these two FSM to build the entire FSM, right? So you can find the FSM2 module. So this module is the thumb module of these two FSM modules. So thumb module means that this thumb module is the upper module. So this is the hierarchical design. So under this thumb module, this thumb module instantiate the sub modules. Okay, so it means that you need to instantiate these FSM mode and the FSM light module under the FSM2 module. Also, you need to connect the required ports and the internal nodes. So you can find the internal nodes here, and so you can build the vector FSM like this. Okay, this is the hierarchical design like the first path of lab assignment number 2, right? So in the first on the first task of the lab assignment, you are requested to design structural model, right? So structural model includes the multiple sub-modules, and then multiple sub-modules are instantiated under the thumb module, right? So you can design the FSM2 like this. So you can design FSM2 like the structural model. Okay. Then kindly, I also provide the Testbench file. Okay, because we did not learn about the Testbench, and then I will learn about the Testbench during today's class. Okay, and then so there are the 2 tasks there, and then you can just submit your result and then root code, and then generate the BCD file and then output file. Okay. Also, during today's class, we will learn about the Testbench. So actually, you can just read the many Testbenches I provided for this lab assignment. Okay. So you can see the some Testbenches and examples for today's class. Okay. Any questions? No question? Okay. Good. Okay, so in the previous class, we learned about how to design FSM actually, right? So that's why I provide the FSM design assignment for third lab assignment, right? So if you just follow some rules, so we learned in the previous lecture, then you can, I believe you can easily design the FSM. Okay, so as you can see, so this is the example FSM code. So you can find the state register code, and then next state logic, and then output. There is the output. So this is the output logic, and then you can remember that state register is just a group of D flip-flops, and then the input of these D flip-flops are the next state signal. And then the output is the current state signal. So, so actually, as I mentioned, So in this example, so we define state type. So this is the new type, but actually is this statement of this new type does not work well in COSE variable. So that's why I define the local parameter. Okay. So local parameter just define the equivalent character for the some values. Okay, so and then so actually the state register is the date flip-flop. So and then also I showed the example of asynchronous negative reset here. Okay. And then so next state logic, so next state logic generate the this next state signal, and then the next state logic is the combinational logic, and then you can easily implement this next state logic using case statement, right? So this is the example. Also, the upper logic is the so this is the word percent. So you can also generate the output signal using the current state signal only because this is the word percent. So because the output signal is just generated using current state. So as you can see, this is the output logic, the example. So this is also combinational logic, and then as you can see, only the state curve. So this is the current state is used as the input of output logic. Okay, so and then actually in the Billy machine, the Billy FSM, you can find that state curve. It should be a state curve and then another input. Input state, the current state and input signals are used as the input of the output logic. So this is the Billy machine. Okay. And then we also learned about the parameterized module. Okay, we can define the parameter like this. So this parameter is a little bit different from local parameter. The local parameters are only used inside of the module, but so these module parameters are you can just adjust the module parameters when this module is instantiated. So instantiated means that the module is used as an instance, it's a submodule of another module. So that is the meaning of instantiation. So when we define the parameter, if we define a parameter under this force definition, then we can use this parameter for define the parameter for this module. Okay, and then we can change this parameter value when the module is instantiated. Okay. So this is the example that we can just change the width of the input and output ports of MOS multiplexer. So this is and then so in the previous lecture we learned how to design FSM, and then we also learned about the parameterized module, and then let's learn about the module instantiation. So actually, we use the module instantiation many times, in the lab assignment. So actually, I believe you can instantiate the sub modules on your thumb module. So instantiation is actually, I believe you can already know the meaning of instantiation, but instantiation means that so we can design modules hierarchically. So hierarchically means that hierarchical design means that there is a thumb module, and then inside of a thumb module, there can be multiple sub-modules like this. Okay. So multiple sub-modules are instantiated. So it means that it's loaded. So so those modules are included including inside of the term module. So this is the meaning of instantiation. Okay, and then in the digital system design, so actually in the first class of this course, I also mentioned the hierarchy, the hierarchical design. So it means that because so our design, our digital system is very complex. So it is not possible to design entire design using only one module. It's very difficult because the system is very complex. So we designed the smaller and simpler module like the, so we designed the small module and then we just connected up these small modules. And then these small modules need to be included in the some large module, so parent module. Okay, this is called the COM module. Okay, so by instantiating small modules and then connecting these small modules inside of the COM module, and we can design complex systems. Okay, so this is the benefit of hierarchical design, right? So as I mentioned, the current design is very complex. So we can design this complex system using hierarchical design approach. Okay, then let's see how to instantiate the sub-module. So actually there are two methods. So the first method is the positional instantiation. So actually I just showed this positional instantiation as an example until now. So what is positional instantiation is that actually when the module is defined, we also define ports. The ports, so we also define input ports and output ports like this. So you can find that the order of these input ports and then output ports. And then this is the term module. We also declare the internal node like this. So positional instantiation means that we just know the position of this module, right? So the A first, and then B second, the C third, and then Y is the fourth position of this module. So we can just map these signals to the port. The position of the corresponding port of the is instantiated module. So for example, this is the example. So A0 is mapped to the A, port A of this COSE module because the position of this A is here. Okay, so this is A, this is B, this is C, and then this is Y of module COSE. Right. So actually, if we just know the position, so it means that the order of ports in this course declaration of this module, then we can just map the signals to the corresponding port of the instantiated module. So who is the instantiated module? Okay. So as you can see, this is the module name. Okay, so it means that this term module will instantiate the COSE module, and then also this is the instance name. So actually we can instantiate the same module multiple times, right? Because you can just copy and paste the same module inside of the term module. So we also define the instance name. So it means that this COSE module can be used many times inside of the same module. So we also define this instance name. So usually this is not a rule, but usually the instance name starts with U. U means the unit, okay? Unit code and then the number. So, but we can use any name for this instance name. Okay, this is the positional instantiation. So you can just map the signal to the position of the ports like this. Then, okay, this is for the name, instance name. Then what? We can also use the named instantiation. This is the second method for instantiation. So named instantiation is that, so this is the same module, COSE module, and COSE module includes the 3 input ports and then 1 output port. So then you can find the instantiation of this COSE, then you can find that when the signal is mapped to the port of the COSE module, then you can find that it starts with the dot A, and then A0 is here. So when we use the named instantiation, then inside of this module, then we just use the dot, and then it's a port name like A. So this is the port name. And then using the bracket, then we just map the signal that will be mapped to the port of this port. Okay. So this is the signal. So actually it's the same meaning, the A0. So actually this is same to this instantiation. So because the dot A is mapped to the A0 of the display module. Dot B, the port B is mapped to the signal B, and then dot C is mapped to the A1, right? And then dot Y is mapped to the C. So this is the second method for the instantiation. You can use the also named instantiation. So also you can find that. So if we use the named instantiation method, then you need to type more characters, right? So you can think that it's more cumbersome. But I recommend you to use the named instantiation, right? Not to avoid. Okay. So if we use the named instantiation, and we can also implement the unconnected port. Okay, like here. So in this example, you can find that output Y. That Y is not connected to any signal, any node of the distant module, right? So we can just if we just leave this inside of the bracket branch, then it means that this output is not connected to any other internal node. So we can just implement the unconnected port using the named instantiation. Also, so another benefit is that we can reduce the probability of bug. So it means that we can avoid the bug. So it means that actually sometimes you can add some ports when after you design this module, right? So even though actually this module includes the 4 ports like A, B, C, and Y, and then if new port is required, then we can add the new input port like the input logic E. Then if we use the positional instantiation, if the E is included, then we need to figure out the position of new port E, and then we need to map this signal into the position of E, right? But if we just design this module and then this COSE module by yourself, then it's not a problem. It's not a problem. So you can know, new port is inserted, and then we just map this signal to the new position of the new input group, right? It's okay. But usually, like a software, so I mentioned that the current system is very complex, so it means that a system will be designed by many people, many engineers, right? So it means that you can design this module, and then another people can design a module. So what is the problem? Even though you include the new ports on your design, and this information is not updated or notified to the other people, this module design, just forget to add map the new signal to the new port, and it can generate. Okay. So for the module instantiation, so there are two methods, like the positional instantiation and named instantiation. But I recommend you to use named instantiation, even though you need to type more letters or characters. So actually for the lab assignment, I use the positional instantiation. So this is because I do not add the port name. Okay, so I want to design the module to more quickly. But in the real design, I recommend you to use the name instantiation in order to avoid bug. So there are two methods, okay, for instantiation. Okay, so you can read these chapters for the system manual design, and then yes, let's oops, not this. So let's learn about another topic of system value design. Okay. So now, we will learn about Testbench. So actually, what is the Testbench? So actually for lab assignment, I provided the Testbench file, like Testbench module. These Testbench modules start with TB because Testbench is the test bench. So actually, usually the name of the Testbench module starts with TB, about some tested module. Then what is the Testbench? So this is the meaning of Testbench from Wikipedia. So this is the virtual environment. So it's not a real device. It's not a real unit for verification. This is the virtual environment. So it means that this is kind of code or software. So this is the virtual environment. So used to verify. So this is important. So if we design some module, then we need to verify our design module. Why? Because we are human. So it means that when we code some software, or if we just make some module, then our module will include the errors or bugs, right? So in order to remove errors or bugs, then we need to verify our design. Why? When you write the code, then your code will include the errors. Then we can execute the output, and then we can find some errors, and we can fix errors. This is the process of verification. It's also same for the hardware design. So as for hardware design, we can use HDL, so system value or VTPL. And then that means that if we just write the code for our hardware design, then our module or our code will include errors or bugs. Then we need to remove errors or bugs. So we need to verify we need to verify our design. And then for this verification, we need some another module or another code that can be used for verification. So that is the Testbench. Okay, so that's why I provide the Testbench modules for your lab assignment. So you can run your code using your design module and Testbench module. And then Testbench module generate the input signals, right? Input signals, and then these input signals are provided to the your design module, right? Then your design module receive the input signals and generate output signals. Then we can just check the output signals from your module. Then if these output signals are correct, then you can say that, oh, our module is correct. Okay, so that is the process of verification. And then for this process of verification, we require Testbench. Okay, so it's a software product. So verify the correctness or soundness of a design or model. So actually you can use the Testbench code for your software, your application, for your software code or support. For this hardware design, and then we usually require Testbench module. So it means that if you are requested to design a certain module, then you can design the this module, and you need to also design Testbench module. And then also you need to verify your design using this design Testbench module. Okay, so and then usually, and this is a certain experience. So usually the design time and then verification. Design time and verification time is nearly the same. So it means that you need to invest the nearly same time or even longer time for verification, right? So for debugging your software, then you need to also invest some very long time, right? So it's the same to the hardware design. So in the hardware design using the HDL for verification, then you need to also invest the very long time for designing Testbench module and verification, the real verification. Okay, so it will take time. So sometimes your boss request you to design some module during, for example, 1 week. But you may think that, oh, 1 week, that is okay. We can complete our design in 1 week. But it's not true. This 1 week includes the time for verification because you need to generate the perfect design. So usually you need to also consider the time for verification, right? So because the verification also require a very long time. Okay? And then also you need to design also a good Testbench for your verification. Okay? So Testbench is actually very important because the footage is also the same, but for hardware, if the bugs are included in your hardware, we cannot fix it because this is hardware. We cannot reprogram our hardware design. So we need to design perfect module. So it means that we need to also design good Testbench. Okay? So Testbench for hardware design. Testbench is used for functional verification. the functional verification is that it can just verify functional behavior. Okay, so for example, you can find that. So this is the module, and then module includes the input and output and functional specification and time specification. So Testbench means that Testbench is used for verifying this functional specification of your design. Okay, not timing. Because timing is actually considered when your design is implemented using netlisting, using the real libraries. Okay, so Testbench is used for verifying functional specification of your module. And then it's important to cover as many as possible cases. So I explained that when I provide the Testbench for your code, then our Testbench generate the input signals for this module. Okay, but these input signals for this module need to cover as many as possible cases. So what does that mean? So like something like this. So this is the AND gate, and then we want to verify functional specification of this AND gate. And this is the 2-input AND gate. And this input signal can include the 4 possible cases, right? So 0, 0, 0, 1, 1, 0, 1, 1, right? So in order to verify the functional behavior of this AND gate, and actually we need to test these 4 possible cases. Then we can verify the behavior of this AND gate perfectly, right? Well, this is the very simple example. So that means that we can just define all possible cases for this AND gate. But usually our design includes the many input ports, like 100 or 1,000 input ports. Then how can we define the all possible cases? It's not easy actually. But when we design a Testbench, this Testbench includes the as many as possible cases. This is very important actually. This is called coverage of Testbench. So it's not possible. I can say that it's not possible to cover entire pieces for these input signals. It is because in the normal design, the input port, there are many inputs, like 100 or 1,000. And then think about this. So if there are 1,000 input ports, then we need to define to the power of 1,000 cases. Not possible actually. So, but it's important. Your Testbench need to cover as many as possible cases. Okay. And then also this is important to be efficient to verify a code design. What does that mean? So for the previous lab assignment, so I requested you to submit the waveform, right? So actually, then how can we verify our design? So actually the Testbench generates the input signals, and then the output signal is generated from your design. Then we can just display input and output signals in the waveform, right? And then if we just see the waveform, then we can just check the behavior, because the inputs, we can just see the input signals, the behavior of input signals, and then we can check the result from the input signals with the waveform. Then we can verify our design using the waveform. That's why we can keep review stuff with the waveform. But if the system is complex, then it will be very difficult to do. Because there are many signals. Actually you are designing a very simple system, very simple module, but in the real design, our module includes the many signals. And it's not possible also. It's not possible to verify the behavior of many signals using waveform. The waveform can be helpful because we can just check the timing of the signal. But sometimes we need to design the more efficient way to verify our design. So actually, for the second and third assignment, our test bench. So I also designed the test bench for your design, but this test bench stores the input signals and output signals, right? And then you also need to submit is generated out file, right? So in the out file also includes the stores the inputs and outputs. And then I can just check the output signals for your submitted out file, right? And then I can just know the design is correct or not. So we need to design more efficient test bench for verifying our design. Okay, so which means that we can also use the file IO, or we can also use the test vector for our test bench. Also, it's not synthesizable. So what does that mean? Our core design. So for this course, I explained that we use HDL for designing real hardware, right? So it means that our design, our code should be synthesized into the netlist. Okay, so it means that our design should be translated into the real hardware. So we need to consider this synthesis process for this design. But test bench is different because test bench is only used for verification. Okay, so it is not. So actually, we don't need to synthesize the test bench because this is just used for verification. It's a test, and then this is the virtual environment, not a real system. So test bench is not synthesizable. So when we design a test bench, we don't need to consider the synthesis. Okay, we can just write the test bench code like a normal software code, right? So it's not synthesizable. So this is the HDL test bench. So it's an HDL test another module. Then actually this tested module is called the DUT. Okay, so it means the device on the test or design on the test. So that is the tested module. And then this is the rule for the. So it is the types of test bench, the simple test bench and executive test vectors. I will show the examples of these three types of test benches. Okay, this is the structural model of test bench. So actually, I believe you are. So if you read the test bench code I provided, then I believe you are familiar with this structure. So test bench So Testbench module starts with the TB at the bottom module name. So actually, if you read this Testbench code, you can find that Testbench includes the design module. So design module is instantiated under the Testbench module, right? So this is the structure. So under the Testbench module, there is a core design, which is the UUT, design of the test or UUT. Sometimes it is called UUT because it means the unit under test. And Testbench generates the input signals. Okay. Then these input signals are mapped to the input ports of DUT, design of the test. Okay. And then input signals are provided to the input ports of the code design. And then output port is just generated from an enzyme. Then output port is also connected to the signal under the test bench. Then if you see the test bench file, then you can find that Testbench module does not include any input and output ports, right? So it looks like this. So there are no ports in the Testbench, and then Testbench just generates signals inside of the Testbench module, and then generating signals are given to the input ports of the code design, and then output signals are generated, and then the Testbench monitors the generated output signals from the DUT. So this is the common structure of the Testbench module. So sometimes we can design the Testbench like this. So Testbench has the input and output port, and then the DUT is connected to the Testbench like this. But usually we use this model. Okay, Testbench does not include the any input and output ports, and then actually the required signals are generated inside of the Testbench, and then these signals are provided to the input and output portion of the DUT. So it is because in order to implement this model, then we need to also include another hub module for this Testbench and DUT connection. So usually we use this model or this structure for designing Testbench. Okay, so let's see the example. So this is the example of the Testbench. Okay, so as you can see, the Testbench module is named of the Testbench module is the TB underbar MOX2. Okay, it starts with the TB. TB means the Testbench, and then it's a MOX2. So it means that you can know that this Testbench is for this Testbench is designed for verifying MOX2 module, right? Okay, so usually we use this name convention. The Testbench starts with the TB, and then it includes the name of the module, which will be tested by this Testbench module. Okay? And then, as you can see, there are no input and output ports. Okay. And then signals are declared inside of this Testbench module. And then, as you can see, this is the DUT. So module name of the design of the task, the MOX2, and then this is the instance name of MOX2. So usually we use the DUT as the instance name of this module which will be tested. And then the input and output ports are connected like this. So internal signals and here. So these are connected to the input and output ports of MOX2. Okay. Then what's this one? You can find the new statement, initial. Okay. So actually we learned about the arrays, and also we learned about the assign. So it's a continuous assignment, and arrays is the actually the arrays where we just define the sensitivity list, and then the sensitivity, the condition of sensitivity list is met, the arrays is executed, and then you can just new statement initial. So what does that mean? Initial. Actually, the behavior of initial is similar to the arrays, but array execute is inside the statement when the condition of sensitivity list is true. Initial means that when the simulation starts, then this statement is executed and done. Okay. So initial means that this statement starts at the beginning of the simulation and it is executed. So you can find the many initial statements inside of the Testbench code. And then actually initial statement is not will not be synthesized. It is not synthesizable. Okay. So you need to remember that you can use the initial statement using system value, but the initial statement is not synthesizable. It will not be synthesized. Okay. It can be used only in Testbench. Okay. So this is the initial statement. The initial statement is similar to array, but it executes once at the beginning of a simulation. Okay, this is the definition of initial statement. Now you can also find many initial statements inside of the Testbench. Okay, so that's the meaning of this initial statement. So when the simulation begins, okay, if simulation starts, then this line, this statement is executed. Okay, so we just initialize the value of signals, the internal logic, internal signals, right? And you can find the delay. So when the simulation starts, it is executed. But this line is executed at the 10 unit time. Okay. Okay. So at the 10, if the unit time is 1 nanosecond, then it is a nanosecond. Then at the 10 nanosecond, then we can change the value of signals like this. And also another 10 nanoseconds, 10 unit time. And we can also change the value of these internal signals. Also, you can find another initial here. So this means that one at the beginning of the simulation, this statement is executed. So this is the initial statement. So in the Testbench, we need to generate input signals, but this is the hardware, and we can change the input values by time. So not to generate some input signals, so it means that the signal values of input signals are changed by time. Then we can use the initial statement and delay control here. Okay, so we will learn about this delay control later. Okay, so this is these are what I explained. So generally, the Testbench does not include any input and output ports, and then DUT. DUT is instantiated under the Testbench module, and then so DUT is instantiated, and then input stimulus. Input stimulus is generated. So it means that input signals are generated by fan. Okay, and then we can also use the special functions for verification. So in this example, I use the monitor function. Okay? I'll also explain about these special functions later. Okay. So let's see the simple example of test bench code. So this is the simple test bench. Okay, so this test bench just generate the input values like here, and then the output. So actually A, B, C, these signals are connected to the input ports of the DUT, and then this output. Output is just also connected. And then when the test bench is designed, we just design the changes of input values. Then how can we check the correctness of our design? So like very so the input signals are provided to our DUT, and our design will generate output signal. Then using a waveform, and we can check the output value, and then we can check if the output values are generated correctly or not. So this is the very simple test bench, but so it's not efficient, right? So we need to check the correctness of output signal using our eyes. Okay? This is not efficient, right? And then this is not smart. Then how can, so this is the self-checking example, self-checking test bench. So this in this test bench, this is the same DUT, and there will be just define the input and output ports, output signals like here, and then we can apply inputs, and then we can check the generated output. So this is the example. So initially the A, B, C are defined as zeros, and then so this is the simple one, some module, the select function. And if the input is given, then output will be generated. And we can check the desired output values. Okay. So if the output is not 1, then we can display. So this is the input signal. And then for this, in this case, this design works incorrectly. Okay, you can display 0, 0, 0, fail. Okay, and then we can change the input values like here, and then we check the output, and then if the output is not correct, then we can display a fail. So if we use this approach, then we don't need to check a waveform, right? Because we can just check the desired output using the output of the DUT, and then if this output is equal, then we can just display false. This DUT works incorrectly. Okay, so fail. So another way is another approach is to use test vectors. Then what are test vectors? So if we write a test bench code like this, then you can find, oh, it can be convenient, but it's not also. So we need to write include many lines for this test bench. So it means that we can manually check the output of this DUT. Then, for more convenient approach, then we can use the test vectors. And then test vector includes the inputs and then expected outputs. So this is test vector 5. Okay, let's see the example. This is the example of test vector 5, right? And then this test vector 5 includes the input signal, input values, and so these are input values, and then this is the output values. Okay. And then actually we can generate these test vectors using software, right? So we can generate the C model or Python model to generate the test vector file. Okay, when the test vector file is generated, then we just read the test vector file result. Then we just store these results into array, and then just assign input values from the stored array elements. And then you can just check the outputs. Okay. And then for this approach, we can generate the flexibility. So if you also read or check some previous Testbench file, then you can find that I just generate the flexibility, even though the DUT is the combination of logic. Okay. So this is the Testbench clock. So actually, Testbench clock is used for aligning input signals and then output monitors. Okay. So actually, we can assign input signals on the right edge of the clock, and then we can check the output of the output from our DUT to the falling edge of the clock. Okay. So I will explain why we need to check we need to generate the input signal at the right edge of the clock, and then why we need to check the outputs on the falling edge of the clock later. Okay. But using the clock signal, that we can just align the input signals and then monitoring of output signals. So this is the test vector file. Then we can generate the clock like this. So clock signal works like this one. Okay, and then we can find how to generate the clock signals. Okay, so you can find the initial statement here. Initially, the clock value is defined as 1. Also, you can find the array statement. So you can find the array state condition of this array statement, but you can find that this condition is a little bit different, right? So usually when we use the array statement, we use array statement like arrays at and condition of sensitivity list. Okay, so actually n means that in this condition, the value of signals. And but if we use the sharp sign, it means the delay. Okay, so if you see that this array statement, so it means that for delay of 5 unit time, so if the unit time is nanosecond, it means the 5 nanosecond, then the value of clock is inverted. So it means that at every 5 nanosecond, the clock value is inverted. That is the meaning of this array sharp 5. So using this array statement, we can generate the clock signal. Like this is the 5 nanosecond factor. So it is 1 initially. So it's 1, and then after 5 nanosecond, so this is 5, then it is inverted. So it goes to 0. And then after 5 nanosecond, it is inverted, it goes to 1. So we can generate clock signal like this. And clock period is 10 nanosecond, right? Because this is 5 nanosecond and this is 5 nanosecond. So we can generate the clock signal whose period is 10 nanosecond. Okay, so this is the clock signal. Then we need to read the test vectors from test vector 5. Okay, so this you can also find the initial statement here. So initially, so when at the beginning of the simulation, then this command is executing. So with main B instead, it means the binary data or binary signal from this file, okay, by line, and then this is stored in the test vectors. So you can find that test vector is declared like this. So you can, so I believe you are familiar with this one. So it means the 3 down to 0 for this one. So after the name of the signal, you can also declare this signal as the array. So it means that this array includes the elements number 0 to 10,000. So 0 to 10,000. So it means that this array, the test vectors, has the array so test vectors. This is the array number 0, and then this array. So each element of this test vector array includes the 3 down 0 element. So it means that 4-bit signals. Okay, so test vector 0 includes the 4-bit signal. So 1 includes the 4-bit signals. 2 includes the 4-bit signal. So if we declare logic like this, then we can also declare the array. Okay. So this is the test vector file. So you can find that several lines. There are 8 lines. The test vector file. So these are input values. This is this speed is the output, the desired output. So it stores these input values and output values in the test vector array. And then, so the vector number, the index, and then errors are declared as 0. And then we just define the reset signal. Okay? Because we define the clock, then we can also define the reset. So it defines the initial state. Then you can find this module. So what does that mean? Positive edge of clock. So positive edge of clock. So this is the clock signal. At every positive edge of the clock, and then just after the small delay. Okay. So this is also important. After the small delay, we just provide these signals to the input of the DUT. Okay, so this is the test vectors. So from the test vector elements, like the test vector is detected by vector norm. So using this from the test vector element, so we just extract the signal values, and then these signal values are provided to this signal. Okay, but as you can see on the right edge of the clock, and then after small delay. So it looks like this is the rising edge of the cloud, and then after very short delay, then input is provided. I will explain the reason of this signal delay later. Then we can provide the input signals to the our DUT from the test vector. Then, oh, it's a little bit long. Then we can need to check our output from the DUT and then desired output. So which means that we can compare the output from DUT with the desired output from test vector. So as you can see, the Y desired are also read from the test vector, right? So then we need to check the output of the DUT using this desired value. So you can find that is checked at the falling edge of the cloud. Okay. So at the falling edge of the cloud, then we just check the output from DUT. So it is because it's a rising edge of the cloud, just delay. The input is given, then the output will be generated. Okay. But the output is just checked at this point after some delay from the input. Okay. So if the state is not reset, so we just skip during reset. Then we check the Y is the output from DUT, and then Y is compared with the Y underbar desired. Y underbar desired is extracted from a test vector, and then if it's not equal, then we just display error. Okay, so you can find that this display is very similar to the printf function of C. So you can find that you can display errors, and then error count is incremented. Okay, and then we just change the index number, and but the test vector structure is the upload value because there are only 8 lines in the test vectors. Then we just start the simulation. Okay, this is how we use the test vector for generating the test bench. So usually we use this approach because so you can find that this test bench code is more complex compared to the simple test bench. But you need to remember that if we design a more complex test bench, then we can verify our design more efficiently. So which means that we can just generate the test vector from our model, and we just compare the output from our DUT with the desired output from the test vector. And then we don't need to check the waveform actually. We just check the output, and then if the error is detected, then this event is displayed automatically. Okay. So we can write the test bench code more smartly, more efficiently. Then we can verify our design more efficiently without checking waveform. I think checking waveform is not convenient, right? We just check the values, but it's manually check the value. It's not convenient. But using some more smart test bench code, we can verify our design more efficiently. Okay. Okay, so this is the example of test bench code, and then I will explain about some syntaxes in the next class. 감사합니다.